All right. I'm going to assume that as no. So let's kind of recall where we were. So last time I introduced the idea of a primary decomposition, right? And so, and I claimed that in Noetherian rings, so that, you know, so this is about a decomposition of an ideal into a finite intersection of primary ideals, and the primary ideals, yeah, that it's essentially showing that there, you know, the scheme has finitely many irreducible components. And okay. All right, and this was the statement here, and then we did a little bit about primary ideals, right? Some basic properties, and I showed you that primary decompositions are not unique via this example. All right, so now I'm going to start moving into there's a couple things that I want to prove, right? And to prove them, I need to talk about this operation called saturation. Right, so saturation is an operation that allows you to kind of pick out components of your primary decomposition. Yeah, so then after that, we're going to prove existence, right? And then we're going to prove that the collection of associated primes is unique. Although, so that's the associated primes, not the associated primary ideals. So even though the primary decomposition is not unique, right? The primes below each of the primary ideals, those are unique. What is also unique is the minimal primary ideals, or the isolated components, right? So the only non-uniqueness that you really have, it has to do with these embedded components, which are like in kind of the major components, or the isolated components. There can be like little fuzzy bits, right? And those little fuzzy bits are what's not unique. Although we do know the prime ideal that they're going to be below. Okay, so let me just kind of start, and we're gonna do saturation. Okay, so this is about saturation. I guess we'll just do one. Okay, so the motto here is this gives us a way. So let's do it like, let's get a better motto. So saturation picks out primary components. Okay, so if you have an ideal and you want to get rid of like a piece of it, that, you know, we're going to use this operation of saturation. Okay, so let's start with this colon operation first. Okay, so recall. So we had some exercises on this. That if A is a ring, I is an ideal in A, and S, a subset of A, is a multiplicatively closed subset, then I'm going to sneeze. Then we had this colon ideal, I colon S. This is equal to the set of, let's say, Y in A, such that there exists some S in S with SY an element of I. Okay, so this is the way that you should read this is, so these are the colon ideals here. Okay, and the way that you should think about this is like, so you think about this as like I divided by S. Okay, so this is so maybe I should put this in some sort of bubble. Okay, this operation makes the ideal bigger. This makes the ideal bigger. Okay.
The ideal I bigger.
Yeah. So it contains I. So what we're doing is this is what it is we're saturating I with respect to S. Okay. So I wanted to okay. Yeah, I'm going to say that in a second. Yeah, so this, I guess we could have defined this to be the saturation. There's another definition that I'm going to do, and that's equivalent to this definition. Okay. But yeah, this is the saturation operation with respect to S. In the special case, okay, so let me just do some notation. So if S is just a one element set X, then we will let this thing I colon X be oh, let's see. I guess it doesn't have to be multiplicatively closed. I guess is just a subset. Any subset. Then you can do this. Okay, so it doesn't necessarily have to be multiplicatively closed. Okay, then this thing here is X. So this is the set of Y and A such that Y times X is in I. Okay, so this is the colon operation. Okay, so okay. Maybe we should do an example. So let's let A be the ring K of XY. Let's let I be the ideal XY. Okay, and so this ideal again is the inside of spec. It's the inside of a spec of inside A2 of K. So that's spec of this ring, spec of A, right? There's these two axes, right? The X and Y axis. Okay, and so if we do I colon X, so this is the set of Z in A such that ZX is in I. Okay, so in particular, this thing contains Y.
Is that a definition?
This is the definition. This is the definition. I'm just applying the definition here. I'm applying the definition above. Okay, so here what I'm going to show you is, what I want to show you is that this thing here just picks out the x-axis. So I claim that this thing here is just, so the claim here, this is that this thing is just y. Okay, and so you can clearly see that y times x is in I, right? So this implies that y is in IX. Okay, so what this did is it deletes. So this procedure here, saturation. So okay, so what is the axis where y is equal to 0, right? That's just this here. It's just this thing. So saturation will delete. So it deletes this line. What's going on? Is it being weird on your screen too?
I can't tell what it says. Saturation slash something long ideal.
Colon ideal.
Colon. Okay.
This line. Okay, so my stream is kind of messed up. Is it messed up for you guys?
Looks normal to me.
Really? Okay.
No, that's good.
Okay, so it's all like freaking out. Okay, so I might have to restart in a second if it keeps doing this. But it's like flashing on my screen. Okay, anyway, so this is the example here. So do you guys see what happens? So this line here is the line y is equal to 0. So this line here is just the ideal here. Okay, so let's do some basic properties. Okay, so lemma. Okay. Why is it doing that? Okay. Okay, so like QB, maybe I just need to not look at my screen. So let Q, so let A be a ring. And so let Q be a P primary ideal in A. Okay, so 1. You know what? I am going to restart it because I'm worried that the recording is going to get really messed up. So let me just restart this thing real quick. Okay. All right, so sorry about that. Okay, so I was about to show some properties of the colon ideals. Okay, so first, the first thing is that if X is in Q, right, this implies that this thing is 1. The second, so if you're in Q and you saturate, or you do the colon ideal with respect to X, then you just get 1. Okay, if X is not in Q, then this implies that this thing here is P primary. The third thing that I want to show is that if X is not in P, then this thing is just Q. Okay, so it'll pick out okay, it won't pick, so another property that'll happen is that this will distribute over intersections. Okay, and that together with this property is what's going to allow us to pick out primary ideals. Okay, so let's do the proof. Okay, so the first one is pretty straightforward. Okay, so here if you just think about it in terms of division, it makes sense because, you know, if X is in Q, then you're dividing by something in Q, then you should kind of expect there to 1 to be in there. Okay, but let's just write it out. This actually doesn't use the fact that Q is primary. This is totally general, right? So again, we're just going to keep writing out this definition. So yx is in Q, right? So this is the set of y such that yx is in Q, right? But if x is in Q, then this is a vacuous condition. Then xy is in Q for all y, right? In particular, this means that 1 is in this ring, or this ideal. So one of the exercises was showing that these things were indeed ideals. That was from early homework. Okay, so 1 is in there, and so this proves that. So that's how you show something as the trivial ideal, right? All right. So that's the proof of the first part. Okay. Now we need to show that if X isn't in Q, then this thing is primary. Okay. So the idea for this one, so to show that Qx is P primary when X is not an element of Q, right? So this is saying that this is almost saying that this is, so this is saying that when X is not in Q, this is very similar to Q, okay? Okay, so to show that this is P primary when X is not in the Q, we sandwich this thing, okay? And what do I mean by that? So we'll have Q. This is going to be contained in this thing. So I told you it always gets bigger, right? And this is going to be contained in P, all right? And so this thing is going to imply that the radical of Q is contained in the radical of this thing. And this is contained in the radical of P. But since P is prime, it's automatically radical, okay? And so the one thing that I didn't really explain is this part here, that this is contained in P. Okay, so let's do the proof of star. Okay, all right. So, okay, so again, we suppose that X is not an element of Q. Okay, so if y is in Qx, then by definition, yx is in Q. So you can already see that this is like kind of tailor-made for that definition of primary ideals, where if you multiply two things and they land in the primary ideal, then what about the power of one of them? Either one of them is in the ideal, or a power of the other one is in the ideal. Okay, so let's probably so if we have this, then by definition this is in this. This is xy, yx is in Q, and so this implies that x is in Q, or y to the n is in Q, right? And so we suppose that x was not in Q, right? We must have y to the n is an element of Q, right? So this implies y is in the radical of Q, which is P. Okay, so hence we've shown that every element of this is in P, so hence we have this is contained in P. Okay? Does that make sense? Okay. Let's do the third part. Okay, let me remind you what the third part is. The third part is that if x is in P, then the x divided by q divided by x, the colon ideal with q and x is q. So it's the same. Okay, so what we're going to do is so we clearly have, so suppose x is not an element of P. So we always have Q contained in Qx. Okay, so we need to show that Qx is contained in Q. Okay, so we need to show that the colon is contained in Q.
Can we see the definition again?
Yeah. Of this ideal?
Q colon X.
Yeah. So by definition, Q colon X is the set of Y. So let me write it like this. Okay, so by definition, so Y is an element of this thing if and only if Yx is an element of Q.
Okay, right.
Right? Okay, so this implies, okay, this means by Q being primary, that Y is in Q, or X to the N is in Q. But we have that Q is contained in P, which is radical, and hence X to the N is in P. So sorry. So hence so X to the N is in P if we have this, if X to the N is in Q. Okay, but because P is radical, this would mean that X is in P, since prime ideals are radical. Okay, and but this is but we suppose that X wasn't an element of P, so X to the N is not an element of Q. All right, that means that we must have the other condition, right?
What does it mean for an ideal to be radical again? Is that like
Yeah. So an ideal,
like,
an ideal is radical. So good question. So an ideal I in A,
if it equals
radical.
it's radical?
Yeah.
Okay.
If and only if I is equal to the radical of I. Okay. Another way of saying this is that this is if and only if A mod I is reduced. If and only if A mod I has no nilpotent elements. Okay. All right. So suppose that we have this. Okay. So this gives that this means that we must have Y is an element of Q. Okay. And then what were we trying to prove this whole time, right? So hence, if Y is in QX, this implies Y is an element of Q. And this whole thing is equivalent to, QX being contained in Q. Okay, which is what we wanted to prove. Okay, so now we kind of have some nice properties about how primary ideals behave with respect to this operation here. Okay, so back to that example. Okay, let's use this. Okay, so again, so we're going back to this thing here. right? Okay, so we have this ideal. So xy is x intersect y. Okay, and oh, I guess I need one more property. So maybe there's an exercise here. Okay, so the intersection, if I have it, but intersection of ideals of I, and I saturate with respect to x, or I divide with respect to x, or I take the colon ideal with respect to x. This is the intersection of these. Okay. So there we go. Oh, I here. And so this is straightforward. Okay. So and then what did we saturate by? We saturated by y, I think, or did we saturated by x? Okay. So this means that this is I. Right, and this looks like I1 intersect I2. Right, so I colon x is I1 colon x intersect I2 colon x. Okay, and so so here, this thing here is just 1. So this is by the lemma, and this thing here is just y.
Wait,
So
is I1 and I2, those are the ideals generated by X and Y, or?
Yeah. Sorry, I1.
It's been a while since I checked that the product of X times Y is the intersection. Is that true for any ideal?
No, this is so it's not true for any ideal. For any ideal we have so we always have that the radicals will be the same, but this is for this is for this ring. Right? So yeah, as a warning, it's not in general true here. That ij is equal to I intersect j for I and j ideals. Although we did have an exercise before. The radical of ij is equal to the radical of I intersect j. Right? So they're close, right? But they're not the same. They're the same up to nilpotence. Okay, but for this ideal, it's true. Okay. Good questions. All right. So yeah, so you can easily see it's in there. So what we did is when we saturated with respect to x, it deleted this x part, right? So it deleted the y-axis, right? All right. All right. So there's an alternative description of saturation, which I want to give. Okay, so here's the definition. Okay, so let S. So let's let A be a ring. A be a ring. And let S be a multiplicatively closed set. A multiplicatively closed set.
Does it have to include 1 then, or not necessarily?
So it depends on your who you ask, right? In this class, I assume that they always contain 1, but I think if you localize with a multiplicatively closed set, yeah. So yeah, I mean you can always throw in 1 and it doesn't hurt anything. Yeah. So I guess you should have 1. I think. Okay. I mean, I think that we assume that at the beginning, But yeah, let's take them all to have 1. If you had 0 in there, there's a convention where if you localize at a multiplicatively closed set with 0 inside of it, then the ring is 0. All right. Okay, so then the saturation of of an ideal I with respect to S is this operation sat S of I. So this is going to be equal to LS inverse of I times AS. Okay, so it's the inverse image. So what you do is you take the ideal, you stick it into its localization, and then you take the pre-image. Okay, so this is the saturation. All right. So note that Atiyah McDonald used the notation S of I. Okay. For this saturation. So I think Stillman uses this sort of notation. Stillman is the guy. He's the guy who wrote. He's one of the authors of Macaulay 2. Okay, so Macaulay 2 is a computer algebra system for algebraic geometry and commutative algebra. Okay, so it's like CoCalc or Sage. So let's do a lemma. Okay, so let S be a multiplicatively closed set. Let A be a ring. And S a subset of A multiplicatively closed set. All right. And so let I be an ideal in A. Okay. So then the saturation so this is equal to IS, which is equal to the union of S and S of IS. Okay, so this is what the saturation is. So this process of like localizing and then contracting the ideal is the same thing as saturating with respect to the multiplicative subset. Okay. All right. So let's prove. So we kind of have 2 inequalities. Okay. Did I already? I feel like I already wrote that down somewhere. I did not. Okay. Well, that one's pretty easy. It just has to do with the fact that existential quantifiers are really just unions, right? So the proof of star 1. Okay. So I S. So this is just a straightforward application of the definition. All right. So that there exists some S in S such that YS is in I. Okay. So now there's this existential quantifier, right? And so that's exactly equal to the union over S and S. Y in A, YS is in the ideal. Right? So that proves the first thing, and it's completely straightforward. Okay. And it doesn't need to be a multiplicatively closed set here. That's totally general. Okay. So the proof of star 2 is a little more complicated. Right? Okay. So the idea is that the idea is that okay, so the idea here is that LS inverse of I times AS is the kernel.
Can I ask if like I colon A would be I, right?
I colon A would be A.
Would be A, right, right. Everything
Oh,
that
sorry.
okay.
Why did I write that? No, we don't want to do that. Yeah, I colon A would be A.
Right. Okay.
Because whenever you have something, whenever you're dividing by something that's already in the ideal, you'll get the unit ideal or the whole ring.
Okay. Right.
So this thing is the kernel of the map here. A maps to A of S, so the localization here. And then we mod out by the ideal. Okay. Okay, this is again, this is what we define to be the saturation.
And LS takes A to A over 1.
Yeah, this takes A to A over 1. And then this thing maps A over 1 to its like equivalence class here. Okay. So yeah. So this is what we have. Okay, but now we're going to use the property of localization, right? So note this map factors. So we have that so AS mod IAS. This is the same thing as S inverse of A mod I. And you could take this to be the image in the quotient as well. Okay, so this is one of the properties of localization that we had. Okay, so so we have that Y is an element of the saturation.
I'm sorry. What is S inverse?
At localization. So remember that AS was S inverse of A, and IAS. So this is like S inverse of I guess. So all I'm doing is the fact that localization commutes with quotients.
Okay, right. Okay.
Okay, so that's one of the things that we did, and this is extremely useful property. Okay, so that's what I'm doing here. So this thing is isomorphic to this. Okay, and so so this is in here if and only if the representative here, I guess we could call this y bar in A mod I, is in the kernel of A mod I, S inverse of A mod I. Okay, so what I've done here is I've factored this into two different ways. So we're using this idea that so we have this map A. You could go to A to AS. This could go to A mod I. This could go to S inverse of A mod I. Right, and this thing goes to. So we have this commutative diagram like this. Maybe let me write it a little bit longer. So it's more. And then this thing is S inverse of A mod S inverse of I, and these two things are equal. Okay, and also I guess this is S bar inverse of A mod I if you want. These two things are the same. Okay. Okay, so we have these two things. Okay, so so I'm using the factorization. There's a commutative diagram where you can. So if you're modding out by an ideal that you localized at, that's the same thing as localizing and then modding out by the ideal, right? or sorry, localizing and then modding out by the deal, or modding out by the deal and then localizing. They're the same. Okay, so that's why we have this. This is the kernel of this localization map. So maybe I could do a bar here. We could call this L of S bar. But then we knew what the kernel of this thing was, right? So this is if and only if S bar Y bar is equal to 0 for some S bar and S bar. So do you guys know what I mean by S bar? So S bar here is the image of S in A mod I. Okay. So this is kind of like side notes here. Okay. So, and this means that this is if and only if sy is equal to 0 for some s and s. Or sorry, is in I. And right, and this is the same thing as y being an element of is. So this colon ideal. So that proves that these two statements, y being in the saturation and y being in this colon ideal, are equivalent. All right. Okay. So that kind of wraps up what I want to say about saturation. And then next time we're going to use this to show uniqueness of the primary decomposition. Okay, so we now have a way of like, so the idea here is that, again, go back to this one example, right? The idea here is that you get to delete components, right, by doing these colon operations. All right. So
is that the intuition behind the word saturation?
Yeah,
then
yeah, the intuition behind the word, yeah, it's like well, I guess the saturate. So the saturation is a idempotent operation. So like you apply it twice and it'll get back to itself. But I guess the idea is, I don't know why. I mean, it's like you're adding more stuff. Like I think it's like this. It's like here, right? You're adding as much stuff as you would get from localizing. So you're kind of like adding all the stuff to the ideal that you would have gotten if you had just localized the ring.
makes sense. Okay, yeah.
Right? So, yeah. Okay. So, yeah. So, I mean, and this is the other thing that I was saying about, like, it's like you should think of the colon ideal as like adding denominators, but not really, because you are literally adding denominators in this localization thing, but then you just take the inverse image. Okay, so yeah. All right. So yeah, we'll continue with the existence and uniqueness of the primary not the uniqueness theorems, not that it's unique, but the existence and uniqueness theorems for primary decomposition next time. So as usual, I'm going to be here after if you guys have any questions.